Good morning, students. So, once again, we are going to continue into the gravitation chapter. The next concept I am going to continue today is the gravitational potential energy and escape velocity derivations. So, already you know what is potential energy. That is the energy which is due to the position of the body from the surface of the earth, as well as due to the change in the size or shape of the body. So here we are going to derive the expression for gravitational potential energy. So in the discussion of the kinetic and potential energy, I have explained you. So that is gravitational potential energy. So and another type of potential energy. So that is we have discussed in the previous work energy chapter. So here, if the body is moved above the surface of the earth, so let us consider this is the earth, and if the body is moved above the surface of the earth, then the body is going to attain the potential energy. So if you know this, if the duster is moved upwards or anybody is lifted above the surface of the earth, then this body is going to gain the potential energy due to its height from the surface of the earth. Then question arises, why this body is going to obtain the potential energy? This body or any body which is lifted above the surface of the earth is going to obtain the potential energy because this body is going to be acted upon by the earth gravitational force. Means the earth is going to exert the force on this body towards downward direction. Therefore, this body is going to be applied by gravitational force. Because of this, the body is going to gain the potential energy. How? Due to the movement of the body above the surface of the earth against the gravitational force. Gravitational force is downwards, but you are doing the work against the gravitational force. Means you are moving the body against the gravitational force. Means the work is done against the gravitational force, so therefore this body is going to obtain the energy. This energy obtained by the body is called as gravitational potential energy. So here what we are going to do here is, so let us consider the body is now at point A, above the surface of the earth at a distance x from the center of the earth. Let O be the center of the earth. Now, what is the force acted upon by the body? So here, let body of mass m is present at A, position A. So therefore, what is the force acted upon the body at point A? That is given by F is equal to G m into m divided by x square according to the Newton's law of gravitation. So let us consider this is equation number 1. So this famous equation already you know, that is Newton's law. So G into capital M, that is capital M is mass of the earth, small m is the mass of the body, x is the distance of the body from the center of the earth. So here after this, let us consider that the body is moved from A to B. So you can observe here that the body is moved from A to B through a distance, small distance, that is called as dx. So therefore, what is the work done? So already you know in the work energy chapter, so work is calculated through the help of the formula, that is force into displacement. So therefore, we are going to calculate the small work done, that is dW is equal to force into small displacement, that is dx. Now this is equal to F is already we know from equation 1, substitute here G into capital M into small m divided by x square into dx as it is. So let us consider this is equation number 2. Now this is small amount of work done in moving the body from A to B. Now let us imagine that the body is brought from infinity to point C. Infinity to point C means point C is very nearer to the earth's surface. Let us consider the body is brought from infinite distance from the earth's surface to the point C. Then what is the work done? Work, very large amount of work is going to be done. So lot of work is going to be done. So therefore we are going to consider that as total work done. Total work done. Or we can consider like this also, that is, let us consider the body is moved from earth's surface to infinity, very large distance. Then also, so we are going to integrate, we are going to add the total work done. It is integration of dw is equal to integration from x is equal to infinity to, that is r. What is r? So that is the distance from the center of the earth to the earth surface, very very small distance. So therefore here infinity to r, g into m, that is total small work done. It is the integration of dw, it is g mm divided by x square into dx. So this is equal to, so g is constant, that is gravitational constant, universal. M is also constant, this m is also constant, mass is constant. Mass will not change with respect to time. Therefore, take them outside. G into m. Integration of x to x from infinity to r. What remains here? 1 by x square. 1 by x square dx. So g mm into integration from x square. So 1 by x square we can write it as x raised to minus 2 dx. So now let us integrate this. So x raised to minus 2 can be integrated as x raised to minus 2 plus 1 divided by minus 2 plus 1. So minus 2 plus 1 is minus 1, x raised to minus 1 divided by minus 1. So here that minus 1 by minus 1 we can take it as outside here, that is minus gmm. So x raised to minus 1 can be written as 1 by x infinity to r. So this is integration x raised to minus 2. X raised to minus 2, so it can be written as x raised to minus 2 plus 1 according to the integration formula. X raised to n, integration of x raised to n is x raised to n plus 1 divided by n plus 1, minus 2 plus 1. So this is minus 2 plus 1 is minus 1, this is also minus 1. So this becomes 1 by minus 1, that into this is minus gmm. So x raised to minus 1 becomes, this is 1 by x. So therefore here minus gmm as it is, substitute here limits of integration, that is 1 by x in place of x. Now let us substitute the upper limit, that is 1 by r. Next minus, this is minus of 1 by infinity. So this is minus gmm divided by, so 1 by infinity, so that is equal to 0. 1 by infinity is equal to 0, therefore minus gmm divided by r. So this is we can write gravitational potential energy with a symbol, that is U is equal to minus gmm divided by r. So this is the final expression. I hope you have understood this. So if you have any doubts, you can comment which equation you are not understood, or if you understood, you can comment. So now let us discuss the another one, that is escape velocity. Escape velocity. So what do you mean by escape velocity, or define escape velocity? Escape velocity is defined as, it is the minimum velocity which is required for any body or any satellite to escape from the earth gravitational force. So that is called as escape velocity. So this is we are going to derive here. So let us consider the body is, now let us consider any chalk piece is thrown upwards. So this chalk piece or any duster or any body which is thrown upwards, that should escape from the earth gravitational force. The minimum velocity which is required for these bodies to escape away from the, or go away from the earth gravitational force, means they should not return to the earth once if we throw them upwards. So that velocity is, that is minimum velocity is called as escape velocity. So now let us consider this is thrown upwards. Then this should be having kinetic energy, because it is moving with some velocity, linear velocity, as well as this, since this is moving upwards because of the height factor, so this is going to obtain the potential energy also. Therefore any body which is moving upwards away from the gravitational force or away from the earth's surface will be having both kinetic energy as well as potential energy. Therefore we can write the expressions for kinetic and potential energies here. So kinetic energy, let it be 1 upon 2 m into b square, that is what is b? Escape velocity. So you know velocity for that is kinetic energy formula. So that kinetic energy formula can be given for 1 upon 2 mv square. So this is m1 upon 2 m into v square. Now potential energy can be written as, so already we have derived here, u is equal to minus gmm by r square. So u I here, I means here initial potential energy, that is minus gmm divided by r, equation number 2. So why it is capital R? Because this is the minimum distance from center of the earth to the earth surface, that is minimum distance. Now, what is initial potential energy? Initial total energy. Initial total energy is nothing but sum of kinetic plus potential. So therefore, add these two equations. So we have added these two equations. So therefore, equation number 3 like it. Now, let us consider the body has reached the height h above the surface of the earth. Means h means small height, it is large height. Then let us you can write the expressions for final kinetic energy, final potential energy. So final kinetic energy can be written 1 upon 2 mv square, and final potential energy can be written as minus gmm divided by r plus h. Now what is total total energy? So add these two equations, we have got this equation number 4. Now according to the principle of conservation of energy, all of you know this, maybe it is initial energy is always equal to final energy. Means the sum of the initial energy is always equal to final energy. Means energy can neither be created nor be destroyed. So therefore, the initial energy, total energy is equal to final total energy. So therefore, we have equated these two equations. So now I have taken this 1 upon 2 mv square is equal to 1 upon 2 m into v square minus gmm by r plus gmm divided by r plus h, because so this is left as it is RHS, take this minus gmm to LHS, this becomes plus gmm by r plus h. So therefore, if you consider here the RHS, that is 1 upon 2 mv square minus gmm by r, so if it is, there is initial kinetic energy formula. So this is if it is initial total energy, if it is very large, means if it is very large greater than 0, if it is greater than 0 initial total energy, then the final total energy or final kinetic energy will not be equal to 0. It is the simple logic, simple understanding. If total initial energy is not less than 0, if it is very higher than 0, then final kinetic energy of the body which is projected upwards will not be equal to 0. So with this condition or analysis, so we can write this 1 upon 2 mv square minus gmm by r. So it is greater than or equal to 0. So therefore v is greater than or equal to, so root of, because it is here v square is there, so therefore v is equal to root of. So this 2 comes to the numerator, 2 gmm, this minus, if it comes to the right hand side it becomes plus, so root of 2 gm divided by r. So therefore v is equal to square root of 2 gm divided by r. So already in the first equation derivation, already we have derived for g is equal to gm divided by r square. So therefore what happens, gm is equal to g into r square. Substitute here, so 2 gr square divided by r get cancels, v is equal to square root of 2 gr. So this is the final expression for the escape velocity. So these derivations, so they are important and the concepts are also important. Now question arises then, how much velocity is minimum for any body to escape from the earth gravitational field? So it is calculated from this formula by substituting the value of g, that is 9.8, and a capital R, that is radius of the earth. So if you substitute and calculate, we will get the value, that is v is equal to 11.2, approximately 11.2, so that is kilometers per second. So the escape velocity for the body is to escape from the earth gravitational force, so it is minimum is 11.2 kilometers per second. So this you have to remember. So let us stop here. In the next class I am going to continue with the other concepts. Thank you.